Let's jump into question number 1.
Sounds good.
It says heat flows from an object at a temperature of 20 degrees Celsius to an object at a temperature of, and then we've got choices.
Okay.
So what's the fundamental rule about heat flow we got to remember?
So heat always flows from warmer to cooler. Always.
Oh.
Think about like a hot pan on a stove.
Okay.
You touch it, the heat goes to your hand, right? Because the pan's hotter.
Right. So if the first object is at 20 degrees Celsius, for heat to flow to the second object has to be...
It's got to be cooler.
Cooler, right. Okay. And looking at our options, the only temperature lower than 20 is 15 degrees Celsius.
Exactly.
So, boom, question 1 done.
Nope.
Okay, on to question 2. This one asks us to convert 35 Kelvin into Celsius. I vaguely remember a formula for this.
Oh, there definitely is. Degrees Celsius equals Kelvin minus 273.
Okay.
And it makes sense if you think about it. 0 Kelvin, absolute zero, coldest possible temperature. That's like negative 273.15 degrees Celsius.
Okay.
So Kelvin to Celsius, you just got to subtract that 273.
Okay, yeah. I'm kind of remembering this now. So for this question, we take 35 Kelvin, subtract 273, we get negative 238 degrees Celsius.
There you go.
Boom. Question 2 down.
Yep.
All right, question 3. Which phase change represents an increase in entropy? Now, entropy, that's all about like disorder, right?
It is. Randomness.
Randomness, chaos.
Think of it like this. You got a super organized bookshelf, right?
Okay.
Low entropy. Over time, books get moved around. It gets messy, less organized.
Right.
That's higher entropy.
Got it. So we got to figure out which phase change leads to more randomness.
Yeah. Solid, molecules packed tight, very ordered. Liquid, more freedom to move. Gas, they're just all over the place. So liquid to gas. Big entropy jump.
Got it. So the answer to question 3 is liquid to gas. Let's go to 4 and 5. These seem similar. Both are about, like, how systems naturally behave in terms of energy and disorder.
Yeah, they're connected. Both getting at this idea, systems want to be low energy, high entropy. Nature's just kind of lazy.
Why is that?
Think about it. Keeping your room tidy, it takes effort, right? But let it go, boom, messy room.
Yeah.
That's higher entropy, takes less energy to maintain.
So for questions 4 and 5, the answer is lower energy and greater disorder.
Exactly.
Okay, question 6 asks, the temperature of a substance is a measure of the pure. What's the best way to describe temperature, you think?
It's the average kinetic energy of the particles.
Okay.
Kinetic energy, that's energy of motion. Hotter something is, faster those particles are zipping around, on average. Different from potential energy, which is stored energy.
So the answer for 6 is average kinetic energy of its particles. Moving on to question 7. The amount of randomness of atoms in a system indicates it sounds like it's about entropy again.
It is, back to that randomness idea. So the answer is pretty simple.
Yeah.
The randomness indicates the entropy of the system.
All right, on to question 8. During which 2 processes does a substance release energy? Now, I remember processes that release energy are called
Exothermic.
exothermic, right? And the 2 processes are freezing and condensation. Bonds are forming. That releases energy. Like when you form a bond with someone, it releases good energy.
That's a cute way to remember it.
Right.
So liquid freezes to solid or gas condenses to liquid, bonds forming, energy's released.
Yeah.
And the opposite processes, melting and evaporation, those would be endothermic because they need energy to break those bonds.
Exactly.
Okay, so answer for 8 is freezing and condensation. On to question 9, it says, at STP, which property of a molecular substance is determined by the arrangement of its molecules? At STP, that arrangement determines the physical state. Solid, liquid, or gas.
Okay.
So packed tight, solid, a bit more spread out, can move around, liquid, totally free, gas.
Got it. So the correct answer for 9 is physical state.
Yeah.
Okay, question 10 gives us a scenario. 75 grams of water increase in temperature from 20 degrees to 35 degrees C. How much heat is absorbed in this process? I'm feeling like we need a formula here.
We do. Q equals M times C times delta T. Q is the heat absorbed, M is the mass, C is the specific heat capacity, which we can find in our reference tables, and delta T is the change in temperature.
Okay, so looking at table B, the specific heat capacity of water is 4.18 joules per gram per degree Celsius. So to find Q, we multiply 75 grams times 4.18 joules per gram per degree Celsius times 15 degrees Celsius, which is the change in temperature.
You got it. And that gives us approximately 4,700 joules.
All right, on to question 11. We need to identify the element that is a nonmetal and a solid at STP. We've got lead, nitrogen, sodium, and sulfur.
Okay, so lead and sodium, those are metals, right? So those are out. Nitrogen is a gas at STP. That leaves us with sulfur, nonmetal, solid at STP.
So sulfur is our answer for question 11. Okay, question 12 wants the amount of heat required to melt 43 grams of solid magnesium oxide at its melting point. It also tells us the heat of fusion is 1.9 times 10 to the third joules per gram.
So the heat of fusion, that's the energy needed to change a substance from solid to liquid at its melting point. To find the total heat, we multiply the mass by the heat of fusion.
Okay, so we'd multiply 43 grams by 1.9 times 10 to the third joules per gram, which gives us roughly 8.2 times 10 to the fourth joules. That's a lot of joules.
It is. Shows how much energy is needed to break those bonds holding the solid together.
Okay, question 13. How much heat is absorbed to completely melt 26.2 grams of ice at 0 degrees Celsius?
Another heat of fusion problem, but this time it's for water. Table B tells us water's heat of fusion is 334 joules per gram.
Okay, so we just multiply 26.2 grams by 334 joules per gram, and we get approximately 8.75 times 10 to the third joules. Getting the hang of these heat of fusion calculations now.
You're doing great. It's all about understanding what the heat of fusion means, then applying it.
Question 14. Real-world scenario time. A person with a body temperature of 37 degrees Celsius is holding a cup of hot water at 44 degrees Celsius, and the air temperature is 22 degrees Celsius. Which phrase correctly describes a heat transfer happening in this scenario? I'm already picturing this.
Me too. And remember, heat always flows from hotter to cooler. So that cup of hot water, it's going to be transferring heat to the person's hand and to the air around it.
Right, so the correct answer is from the cup to the hand, because that's the most direct heat transfer happening.
Okay.
Question 15 asks, when does potential energy decrease at standard pressure? Earlier, we talked about kinetic energy, energy of motion. Well, what exactly is potential energy?
It's stored energy, related to the position and interactions of particles. When a substance gets more ordered, potential energy goes down. Think of a ball at the top of a hill. Lots of potential energy because of its position, right? As it rolls down, potential energy decreases.
Okay, so when does potential energy decrease at standard pressure?
Here, it's liquid to solid. Liquid turns solid, molecules get more ordered, packed tighter, lowers their potential energy.
Okay, I see. So on to question 16. We've got two metal cubes, one iron at 20 degrees Celsius, one copper at 60 degrees Celsius. We need to describe the initial heat flow between them.
Heat flows hot to cold, always. So initially, it's going to flow from that hotter copper cube to the cooler iron one.
Okay,
They'll eventually reach the same temperature, but at the start, copper to iron.
got it. Question 17 asks, which element is a liquid at 1000 Kelvin? Time to consult Table S of our reference tables. For some elemental info, we've got silver, aluminum, calcium, and nickel. We need to find the one with a melting point below 1000 Kelvin, so it'll be liquid at that temp. Aluminum has a melting point of about 933 Kelvin, which is less than 1000.
Perfect.
So aluminum is our answer. It's the only one that would be liquid at 1000 Kelvin. Question 18. Calculate the heat needed to raise the temperature of a 49.5 gram sample of water from 22 degrees Celsius to 66 degrees Celsius.
Back to Q equals M times C times delta T.
Oh yeah, so the mass M is 49.5 grams. Specific heat capacity C of water from table B is 4.18 joules per gram per degree Celsius. The change in temperature, delta T, is 66 degrees Celsius minus 22 degrees Celsius, which is 44 degrees Celsius.
Exactly. Plug those values into the formula. Q equals 49.5 grams times 4.18 joules per gram per degree Celsius times 44 degrees Celsius.
And that gives us...
About 9.1 times 10 to the third joules.
Okay, great. Question 19. When does the average kinetic energy of water molecules decrease? We talked about kinetic energy earlier, energy of motion, right?
Yep. And average kinetic energy, it's directly tied to temperature. Temperature drops, average kinetic energy drops too.
Okay, that makes sense. So the only answer where water's temperature is going down is HOL at 337 K, changes to HOL at 300 K.
You nailed it. Only one where those water molecules are slowing down, less kinetic energy.
All right, question 20, quick one. What is the joule a unit of?
Energy, we've been using it this whole time.
Right. Every time we calculated Q, the heat absorbed or released, it was in joules, like the energy currency.
Exactly.
Okay, question 21, back to entropy. It asks, why does entropy increase when ice melts at 0 degrees Celsius?
It's all about that randomness. Ice melts. Those molecules go from super organized in that crystal structure to way more freedom in the liquid phase.
So the answer is the particles get more randomly arranged, leading to more entropy, like when you knock over a carefully stacked tower of blocks.
Exactly. That's entropy in action. Question 22 asks, which process results in an increase in disorder? We've got options here, including sublimation, going straight from solid to gas.
That sounds pretty disorderly.
You're right. Sublimation skips a step. Particles go from tightly packed to completely free. Biggest increase in randomness, so the highest entropy.
So answer for 22 is the sublimation of solid iodine. Moving on to 23, we've got CO2 going from solid to gas. What's changing during this process?
Biggest change is the arrangement of those particles. Solid. CO2 molecules are all neat and tidy. Gas, spread out, random motion.
So the answer is particle arrangement. Big change for those CO2 molecules. Question 24 asks for the amount of heat required to melt 200 grams of ice at STP.
Another heat of fusion problem. Remember, that's the energy to go from solid to liquid at the melting point. Water's heat of fusion, from table B, is 334 joules per gram.
Right, so we multiply 200 grams by 334 joules per gram. That gives us 66,800 joules.
Exactly. Nice work.
Okay, on to 25. We have data about a metal sample absorbing heat, increasing in temperature, and we got to calculate its specific heat capacity.
Time to rearrange our formula. Q equals m times c times delta T. We need to solve for C, the specific heat capacity.
Okay.
So C equals Q divided by m times delta T.
Got it. Looking at the data, the metal absorbed 48.75 joules of heat, Q. Its mass, m, is 15.1 grams, and the change in temperature, delta T, is 25.0 Kelvin.
Perfect. Plugging those in gives us a specific heat capacity of roughly 0.129 joules per gram per Kelvin.
All right, moving on to question 26, a two-parter. It says, a test tube contains a sample of solid stearic acid, an organic acid. Both the sample and the test tube have a temperature of 22.0 degrees Celsius. The stearic acid melts after the test tube is placed in a beaker with 320 grams of water at 98.0 degrees Celsius. The temperature of the liquid stearic acid and water in the beaker reaches 74.0 degrees Celsius. So we're mixing things up. Cool stearic acid meeting hot water. What happens?
Well, the stearic acid will melt, right?
Right.
And as it melts, it absorbs heat from the water, making the water cool down.
Yeah.
Eventually, they reach a final temperature, 74.0 degrees Celsius in this case, like adding ice to a warm drink.
That's a good way to picture it.
Yeah.
Okay, now for 26.1. State the direction of heat transfer between the test tube and the water when the test tube was first placed in the water.
Back to our principle, heat flows hot to cold, always.
Right, so that water in the beaker, way hotter than the test tube with the solid stearic acid at the start. So the heat energy is going to flow from the water to the test tube, making that stearic acid melt.
Exactly. Heat energy wants to go to cooler places. Flows from that hot water till they reach the same temperature.
So the answer to 26.1 is from the water to the test tube. Now for 26.2, we need to show the numerical setup for calculating the amount of thermal energy change for the water.
Our trusty Q equals m times c times delta T.
Exactly.
All right, so we know the water's mass, m, is 320 grams. Specific heat capacity, C, of water, we can look that up in Table B.
Let me see, Table B, 4.18 JGK.
Perfect. Now we just need delta T, the change in temperature.
Right, we subtract the initial water temperature from the final one, so 74.0 degrees Celsius minus 98.0 degrees Celsius.
You got it. The complete setup is 320 grams, 4.18 JGK, 74.0 degrees C, 98.0 degrees C. That'll tell us how much heat the water lost as it warmed up that stearic acid and the test tube.
Okay, great. Feeling pretty good about this quiz so far. Are you with us, listener?
Yeah, how are you feeling? All right, question 27, it says, solid aluminum has a specific heat capacity of 0.90 JGK. How many joules of heat are absorbed to raise the temperature of 24.0 grams of aluminum from 300K to 350K? Looks like we're back to our good old Q equals m times c times delta T.
That's a classic.
Right. So let's break it down. We've got the mass of the aluminum, that's our m, 24.0 grams. Specific heat capacity, C, that's given to us, 0.90 JGK. And then our change in temperature, delta T, that's 350K minus 300K, which is 50K.
Okay, so if we plug those in, we get Q equals 24.0 grams times 0.90 JGK times 50K.
And that gives us a lot of joules.
It does, yeah, roughly 1,100 joules of heat absorbed.
Okay, on to question 28. This one asks, at which temperature will HGl and HGS reach equilibrium in a closed system at 1.0 atmosphere?
Now, Hg, that's mercury, right?
It is, yeah.
But I'm not quite sure I remember what it means for them to be at equilibrium.
So equilibrium here means the rate of melting and the rate of freezing are the same. So you've got this balance, no net change in the amounts of solid and liquid mercury, even though those processes are still happening.
So it's like it's changing, but it's also staying the same.
Yeah, exactly. It's like a dynamic balance.
I like that.
Yeah.
Oh.
And this happens at a specific temperature. That's the melting point.
Okay. So to figure this out, we got to find the melting point of mercury.
Exactly.
Where would we look for that?
Back to our handy-dandy table S.
Oh, of course.
Gives us those properties of elements. Let's see. Yeah, melting point of mercury. About 234 Kelvin.
So our answer for question 28 is 234 K.
You got it.